So in the previous lecture, we introduced the notion of Lebesgue outer measure. Let me start by recalling the definition. Recall. The Lebesgue outer measure of a set E which sits inside R is defined by M star of E, that's the notation that we give, is equal to summation L of In. N varies from 1 to infinity. Then infimum taken over, let us say, a collection IE, where IE is the collection of all countable family of open intervals In that covers E. Meaning E is contained in union N In. You consider a countable family of open intervals whose union contains E. Find length of the interval in this collection and sum it. Now you vary this countable family and take the infimum. Okay. Let me stress that one member of the family IE would be one countable collection of intervals, In. Another member would be another countable collection of intervals. Let us say Jm, that covers E, and so on. Please don't think In is a one particular member of IE. No, collection N varies from 1 to infinity, is one particular member of IE. Collection Jm, M varies from 1 to infinity, is another specific member of IE, and so on. So each member of IE is a countable collection of open intervals. Then for a particular member of IE, you find summation length In. And then this, you take infimum varying over members of IE. So this was the definition for Lebesgue outer measure that we introduced in the previous lecture. From the very definition, you can see that for any subset E of R, the Lebesgue outer measure is non-negative, right? M star of any E in R is greater than or equal to 0, possibly infinity. We are working on extended real number system. Therefore, you can view this M star as a function. Okay. So let me note it here. Note that M star can be viewed as a function M star from, it is defined for any subset of R. So the domain is the power set of R and the codomain is non-negative extended real number. So M star is a function from 2 power R to closed interval 0 infinity. Please bear in mind that 2 power R is a sigma algebra. 2 power R is a collection of subsets which is closed under set operations, complementation, union, and so on. In fact, that is the universal set for the collection of subsets. Okay. Subsequently, we listed certain nice properties for M star. First one was that M star of empty set, as we expect, is 0. Outer measure of null set is 0. Then we have seen that, in fact, for any countable subset, M star is 0. If E subset of R, E is countable, then M star of E is 0. In particular, singleton set, finite subsets, etc. have Lebesgue countermeasure 0. Since Q is known to be countable, M star of Q is 0. So as far as Lebesgue outer measure is concerned, countable sets are negligible. Their measure is 0. Another nice property that we discussed was the following. If A and B are two subsets in R such that A is contained in B is contained in R, then M star of A, smaller set, is less than or equal to M star of B. We express this by saying that M star is monotonic. Monotonicity of M star. Next nice property that we discussed in detail was the following. Lebesgue outer measure of translation T plus A is same as Lebesgue outer measure of the original set. Okay. Where the translation is defined as usual. T plus A is equal to T plus small a in A. For any subset of R and for any real number T. Since you are in a field R, this plus makes sense, T plus A. And I forgot to mention here one thing. So let me stress that point here. This capital A, okay, for instance, this, now I took a subset of R, but A may be intervals and those intervals may be of infinite length, okay, and we can include the case infinity as an element of A. That case also we can include, but the convention then that you have to take is the following. The convention is t plus minus infinity. If minus infinity happens to be an element in A, then t plus minus infinity is treated as minus infinity for any real number t, and t plus infinity is treated as infinity for all real number t. So this convention you can keep in mind. Therefore, even if A is not subset of R, but it is like intervals of infinite length, something like 0 to infinity, infinity included, then also you can talk about T plus A. Okay, with this convention in mind. So these are some nice properties of M star that we collected in the last lecture. Okay, so we shall go ahead with some more nice properties of M star. So far, so good. Yes or no?
Yes, sir.
Yes, sir.
So these are the nice properties that we expect for any concept of measure, which is generalization of length, should have. Okay. Now let us continue. Next, we have our much awaited result, namely the following. I think I stopped by stating this theorem. The Lebesgue outer measure of an interval is its length. Any interval where even infinite intervals are being included, intervals of infinite length. Okay. So first we shall prove it for closed bounded intervals, and then we will extend it for any kind of intervals. Okay. Proof. Case 1. Suppose in the statement I will add of an interval I is its length. That is, M star of an interval I is same as length of I, where I is an interval. So first I will take I to be closed boundary interval. Suppose I is equal to AB, where A and B are real number with A less than B. Why we want to consider closed bounded interval is, if you see M star definition, you should deal with countable family of open interval that covers E. And in case E is closed bounded interval, this open cover will have a finite subcover by Heine-Borel theorem. So in order to invoke Heine-Borel theorem, we are considering the case closed bounded interval. Okay. Now, I would like to consider M star of I. And as the definition suggests, if you want to consider M star of I, you have to consider countable family of open intervals that covers A. Okay. And then you have to vary this countable family. So let us first think of one countable family of open intervals that covers A. Okay. Consider I1 is equal to, let us say, A minus epsilon by 2, B plus epsilon by 2 for some epsilon greater than 0. I1 is that, and In is null set for all n greater than or equal to 2. Then the countable family n belong to n, is a countable family of open interval that covers I. Do you agree?
Yes, sir.
A minus epsilon by 2. Even single interval in that family is enough to cover closed interval AB. Okay. And for that fixed countable family of open interval, summation length In coincides with length of I1 plus 0 plus 0 plus etc. And length of I1 is B minus A plus epsilon. Okay. Now, what is M star of I? M star of I, by definition, is infimum of such sums. Okay. So, M star of I should be less than or equal to summation length IN for this particular cover. Therefore, M star of I is less than or equal to B minus A plus epsilon for any arbitrary epsilon greater than 0. Therefore, it follows that M star of I is in fact less than or equal to B minus. Quite trivial. Now, in order to prove that M star of I is equal to length of I, in this case, that is M star of I is equal to B minus A, we have to prove the reverse inequality. M star of I greater than or equal to B minus A, and that is a bit involved. Now we prove the reverse inequality. M star of I greater than or equal to B minus A. Now, again revisit the definition of M star I. M star of I by definition is infimum of summation length of In. So if I can prove that for any arbitrary collection In of open intervals that covers A, summation length of In is greater than or equal to B minus A, then is it done?
Yes, sir.
Suppose I can prove that for any arbitrary collection of countable family In of open intervals that covers E, that is, I am taking an arbitrary member of IE, and then I am proving that summation length of In is greater than or equal to B minus A. Then infimum also will be
Greater than equal to B minus A.
okay. So let me write that. It is enough to prove. Is enough to prove that summation n is equal to 1 to infinity L of In is greater than or equal to B minus A for any collection In of, so countable is clear when I write In n element of n of open intervals that covers the set under consideration, namely I. So let us start with one such collection. let sequence in n equal to 1 to infinity be one such collection. In the family IE, here IE is I, the interval I. So we have to prove that summation L of In is greater than or equal to B minus n. Now note that this In n is equal to 1 to infinity is an open cover of I. It consists of open intervals and it covers I. So it is an open cover. And I is compact. By Hannah-Borel theorem, there exists a finite subcover. There exists a finite subcover. Let me call IN1, IN2, so on, INK of the open cover IN. N is equal to 1 to infinity. That is, the interval I is contained in IN1 union IN2 union etc. union INK. Okay, interval I is AB. Remember, each of these INJ, j equal to 1, 2, 3, etc. up to k is open. Okay, so far so good. Can I proceed?
Yes, sir. Yes.
Okay. Now, A is an element in I. Therefore, A should be in one of these sets. INJ. Okay. Since A belongs to I, A must be in one of the INJ for J in 1, 2, 3, etc. up to K. And each INJs are open. Okay. So I will call, let this INJ be A1, B1. Since it is open interval, finite length, and so on, it will be of the form A1, B1. Okay. So you have AB here. This A will be in one of the IN1, IN2, so on, INK. That interval I am calling as A1, B1. A1. B1 can be before B or after B. So let me, so this is one possibility. AB, A1. This is another possibility. Okay. We have A1 less than A less than B1. This much I know. Whether B1 is less than B or B is less than B1, that I don't know. I cannot confirm. But let us suppose if B1 is less than or equal to B. So this case I am considering. This case. I will not talk about the second case now. You will understand why soon. If B1 less than or equal to B, then B1 is in AB and AB is your I. So B1 is a member in I and I is covered by IN1, IN2 and so on, INK. Therefore, B1 should be in one of these intervals. Okay. Since and B1 is not in open interval A1, B1. Since B1 is not in A1, B1 and B1 is in in1 union in2 union etc. union ink, there should exist an interval. There should exist an interval. Let us call it as A2, B2. Such that B1 is in A2, B2. Okay. So this B1 will be a part of one of this open interval. That open interval I am calling as A2, B2. Okay. What does it mean? B1 element of A2, B2 means that is A2 less than B1 less than B2. Continue like this. Continuing like this, we obtain a sequence of open intervals, a sequence, finite sequence, A1, B1, A2, B2, let us say some AM, BM from IN1, IN2, so on INK, such that, see this relation, A1 is less than A less than B1, A2 less than B1 less than B2 and so on, such that AI is less than BI minus 1 is less than BI. Okay. Now, whether this process will terminate in finite number of steps or no. Yes. Can you hear me? Is the question make sense? So I am getting A1, B1, A2, B2, etc. AM, BM. Will this process terminate in a finite number of steps, or I will go on getting the intervals? What do you feel?
So it will terminate.
Why should it terminate? Because I have only finite number of open intervals, in1, in2 and so on, ink. Everything happens inside those. Okay, a1, b1 is one among that, a2, b2 is one among these k intervals and so on. Okay, that means this process should terminate. Okay, since inj j is equal to 1 to k is a finite collection. From countable, we went to finite by using Henneborel theorem. And then everything happens inside this finite collection. Our process should terminate with some AMBM. After some m stages where m is less than or equal to k, this should terminate. What is the meaning of termination? You see, when you can proceed b1 less than or equal to b, you could proceed. And similarly, then next step is here. Yeah, one is this. Let me highlight that. B1 less than or equal to b, then you could get an interval. I could have written one more step. Anyway. So can you tell me, in terms of this relation, this B1 less than or equal to B, B2 and B1 connection and so on, when this process will terminate? Can you tell me? Finally, your B, this B should be in one of these AK, BK. Then only it will terminate. Yes or no?
Yes, sir.
If B1 is less than B, you could get. If B2 is less than B, again you could get. one more, and so on. Okay, so if termination means B should be less than this BM. Okay, and this will happen. This will happen only if B is in AM/BM. That is, AM is less than B less than BM. If BM was less than B, like here, BM is less than or equal to B, then you can proceed and get one more step. But we are saying that it terminates in BM. So this is the possibility. Okay. Now, summation length of INJ, J varies from 1 to K, is greater than or equal to summation length of AIBI. I is equal to 1 to M, because AIBI, I is equal to 1, 2, 3, etc. up to M are sum of the intervals among I and J. So, sum of all possible intervals in1, in2, etc. Ink is greater than or equal to sum of the subcollections of intervals. Okay, and this is equal to bk minus ak, bm minus am, sorry, plus bm minus 1 minus am minus 1 plus etc. plus b1 minus a1. Length of each interval I am summing, and let me rewrite it in a suitable way. Bm minus am minus bm minus 1. I am clubbing these two terms. Next, minus am minus 1 minus bm minus 2, and so on, minus a2 minus b1 minus a1. I just rewrote this. Okay. Now, can I say this is greater than or equal to bm minus a1? Please see the relation between AIs and BIs. AI is less than BI minus 1 is less than BI. This you have in your hand. Okay. So AI minus BI minus 1 will be negative. So each of this quantity, AM minus BM minus 1, AM minus 1, BM minus 2, and so on, A2 minus B1 are negative. Okay. So can you say this total thing is greater than or equal to BM minus A1? Yes or no? Is it clear?
Yes,
Yes,
sir.
These
sir.
are all negative. These are all negative. Okay. And will you agree if I write this greater than or equal to B minus A? So AB was here and A1 was outside A. And when the process stops, BM will be outside B. B is less than BM. So you have this. Therefore, BM minus A1 length will be greater than or equal to B minus A length. Okay. Yes or no?
Yes, sir.
Yes, sir.
Now, summation j is equal to 1 to k L of I and j is greater than or equal to B minus A. And now see this. I is contained in this. Okay. So, length of I. So, do you see that length of I, sorry, M star of I would be greater than or equal to B minus A? So much of technical details are involved. That's why I am trying to ask you again and again. Can you see that from this? Can you see that the length of I is greater than or equal to B minus A? Yes or no? Greater than or less than? Which one you want? It is enough to prove summation length of In is greater than or equal to B minus A. Yeah. So did I make some mistake? So I am getting summation J is equal to 1. Let me write. Thus, let me write the conclusion. Thus, summation J is equal to 1 to K length of INJ, right, is greater than or equal to B minus A. So this is what I got. Yeah, that is summation J is equal to 1 to N L of In. This is a subfamily, finite subcover of INJ is greater than or equal to B minus A. And now this is, sorry, this is infinity. This is true for all. See, this IN I have started with an arbitrary collection. INB, an arbitrary collection in IA. So you take any such collection in IA, I am getting this summation to be greater than or equal to B minus A. This is true. This is true for any arbitrary but fixed collection IN of open intervals covering E. Yes. So I was a bit confused in between covering I. Okay. See, please see the starting point. I started with not, yeah, INB, one such collection in IA. This is arbitrary. I have not fixed any IN. I mean, a special IN I did not take. Okay. So if you want, I can write as B, instead of writing one such, B, an arbitrary but fixed collection in IA. So for any arbitrary IN I am taking, I am getting summation length IN is greater than or equal to B minus A, and that will give infimum of summation J is equal to 1 to infinity L of J is also greater than or equal to B minus A, infimum taken over all IE. But that is M star. M star of I is greater than or equal to B minus A. Sorry for the small trouble in happened in between. I was a bit confused by this statement. This one. I is contained in this. So I was trying to relate it with monotonicity. Then you will get only M star of I less than or equal to M star of this. But I am not considering monotonicity here. So I got that summation length of Ij is greater than or equal to B minus A. And this is true for any collection you start with. Okay. Is it okay?
Yes, sir.
Yes, sir.
So what did you prove? M star of I is greater than or equal to B minus A, combining this star 2, and previously you have already proved this. This is star 1. You have M star of I is equal to B minus A, and that is actually length of I. So measure of an interval coincides with length of the interval if the interval is closed and bounded. Okay, but we have to prove this theorem for any interval. So let us take case 2. Now what I will do, in every other case, I will reduce to the problem of closed interval, because for closed interval I have already proved. Okay, let I be any finite interval. Now I don't consider it to be closed. Length is finite for the time being. Then you can write what are the different possibility. Then I may be one of the form. It may be open AB, this possibility with A, B element of R, A less than B, or it can be something like this. Please try to write all the possibility, or maybe something like this, and so on. Okay, I'm not saying that this will exhaust everything. You can try. So like this, there are various possibilities. Okay, but I'm considering only finite. In that case, this may be included, this may be included, excluded, and so on. Various possibilities. So I make the following claim, which is obvious actually. For sufficiently small epsilon, epsilon greater than 0, my aim is to reduce the problem into closed bounded interval. Okay, A plus epsilon, B minus epsilon. This interval will be contained in I, whatever I you take, and that I will be contained in A minus epsilon, B plus epsilon. Do you agree?
Yes, sir.
Obvious, right? A plus epsilon, B minus epsilon will be here, and then A minus epsilon, B plus epsilon will be greater than it. I may be open, semi-open, semi-closed, whatever it is. Now what I did is, I sandwiched I between two closed bounded intervals. Okay. Now I can apply monotonicity, which you have already proved. M star of A plus epsilon, B minus epsilon, closed interval, will be less than or equal to Lebesgue countermeasure of I, and that will be less than or equal to Lebesgue countermeasure of A minus epsilon, B plus epsilon. Now you can use case 1. Since these are close bounded interval, by case 1, length of A plus epsilon, B minus epsilon, M star will coincide with the length for close bounded interval, is less than or equal to M star of I is less than or equal to length of A minus epsilon, B plus epsilon. Okay, and that is B minus A minus 2 epsilon is less than or equal to M star of I is less than or equal to B minus A plus 2 epsilon. For what epsilon? For any sufficiently small epsilon greater than 0. Remember, epsilon greater than 0 is arbitrary. Okay, and this will give, that will imply M star of I, arbitrary but small epsilon, this is true. M star of I is equal to B minus A for every epsilon greater than 0 sufficiently small. So measure of I is equal to length of I. This is length of I again. So from closed bounded interval, we went up to any finite interval. Now not over. Case 3. Now you consider any interval. Let I be an infinite interval. Finite cases already discussed. Be an infinite interval. Now again I want to reduce this problem of finding M star I to outer measure of a closed bounded interval. So what will I do? Since I is infinite interval, the following happens. Given any real number alpha greater than 0, there exists a closed bounded interval J, let me put J suffix alpha, such that J suffix alpha is contained in I and length of J suffix alpha is equal to alpha. Do you agree? Now your I is an infinite interval, maybe full R or maybe A to infinity or maybe minus infinity to A, whatever be the case. You can always find an interval J alpha contained in I and length of J alpha is alpha. Is it trivial?
Yes, sir.
Now apply the monotonicity. Therefore, M star of I is greater than or equal to M star of J alpha because of M star monotonicity. But since J alpha is a close bounded interval, M star will coincide with the length. And length of J alpha is alpha. So you got M star of I is greater than or equal to alpha for any real number alpha. That is possible only when this implies M star of I is greater than any real number equal to plus infinity. Okay, but also you know that length of I is plus infinity. I is an infinite interval. Therefore, M star of I is equal to L of I. Thus, in all cases, you have outer measure is equal to length. Okay. This is a important result because what you were trying for is to generalize the concept of length. If you want to call something as a generalization, when you take the particular case with which it started, it should coincide. So we started with the concept of length, and length are applicable for intervals. Now, if you find some measure which is applicable for sets other than intervals, for intervals, it should coincide with the length. Okay. So this is an expected result, and it is in fact true. Okay. I will send you a reference where the author proves this result in a much simple way. This is the conventional proof you can see in any textbook. Okay, so I will give you another reference. I will send you. For a short proof of the above theorem. I don't know whether you have a habit of reading articles appearing in American Mathematical Monthly. This is a publication where articles like this, a simple proof or a new proof of some classical theorems, generally get published in this publication, American Mathematical Monthly. Okay, so you please have a habit of looking into this journal, I would say, where articles will be on topics with your which you can reach within your reach, like M.sc courses. There can be some good articles on linear algebra within your reach. The classical theorem, they may approach with different proof, or the classical theorem with a new application and so on. If you want to have, please look into this venue, American Mathematical Monthly. Okay. But this particular reference, in which the author talks about a simple proof for the fact that outer measure of an interval is length, I will send you. It's just one paragraph where he uses the idea of connectedness of the interval. Anyway, But I would like to give a conventional proof which you can see in any book. That's why this. That's also easy. Only thing is that it is bit lengthy and technical. The crux of the matter is Hannah-Borel theorem. That's it. From countable, you went to finite. Is that okay?
Yes, sir.
Have you ever come across this publication, an American Mathematical Monthly? Do you have a habit of reading the articles there? If no, this is the right time to start. Okay? You can see several interesting articles based on just on the courses that you have done, like real analysis, linear algebra, etc., etc.
Okay, sir.
Please have a look into it, especially for those who are interested to pursue PhD and so on. This is the because that will give you an art of reading, how to read articles other than books. Okay. So now next, let me give you a nice application, which at least to me is very appealing for the previous theorem. The previous theorem was telling that outer measure of any interval will be length of the interval. You already saw a result. Countable sets have measure 0, outer measure 0. Okay. So let me recall that. Note that E subset of R, E countable implies M star of E is equal to 0. By this time, you would have noted that a statement P implies Q is logically equivalent to not Q implies not P, which is called its contrapositive. Okay. Therefore, E subset of R, measure of E is not 0, will imply E not countable. That is, E is uncountable. P implies Q is logically equivalent to not Q implies not P, called contrapositive. And you all know that if P implies Q, it is not necessary that Q implies P. That is called converse. Converse need not be true, but contrapositive is equivalent to the original statement. Now this, please keep in mind. Now we have next, I will put it as a corollary of the above theorem. Do you know that any non-trivial interval in R is uncountable? AB is uncountable.
Yes, sir.
Sir.
When I say non-trivial, I mean null set can be treated as an interval. Open interval A. Singleton set can be treated as an interval. Closed interval A. Apart from these two trivial things, any other interval will be uncountable. Okay, that you can deduce from the previous result. Every interval in R that contains at least 2 points. This is what I mean by non-trivial interval. At least 2 points is uncountable. Non-trivial intervals are uncountable. Okay. Now, can you supply a proof? I have already given you the sufficient material. First thing I have told that it is a corollary of the above theorem. And also I have recalled this. If measure is not 0, it should be uncountable. Okay. For an interval, what is the measure?
Length of it.
Length of the interval, you have already seen. So suppose I be an interval. I is an interval that contains at least 2 points. That contains at least 2 points A and B. Let us say A less than B. Otherwise, you can change the name. And so you can always assume A less than B. So I is here and you are taking 2 points A and B inside I. Okay. Then since I is an interval, once A and B are in I, the whole interval, closed interval AB will be inside I. Okay. Then closed bounded interval AB will be in I. Therefore, measure of I, outer measure of I, is greater than or equal to outer measure of AB by monotonicity. But outer measure of AB is B minus A. And B minus A is greater than 0 because A is less than B. So you have outer measure of I is not 0. And that will give you that I is uncountable. Therefore, I is uncountable. In particular, R is uncountable. R can be identified as an interval, open interval minus infinity, infinity. Okay. Thus, any non-trivial interval is uncountable. In R, uncountable. Okay. I find this result very interesting in the sense this is a result which reveals an application of outer measure to a result which is apparently unconnected with it. Uncountability is nothing connected with outer measure. If you see, outer measure is something different, but you could derive uncountability of certain things using outer measure idea. So in that way, it is an application of outer measure in an area which has no direct relationship between the outer measure. And this should signal that outer measure has a deep mathematical applications. It can connect to different areas. Okay. So let us continue our endeavor. Our endeavor was to collect nice properties of outer measure. Let us continue with it. Next theorem. Let sequence n belong to n, be a countable collection of subsets of R. Countable collection of subsets of R. Then Lebesgue outer measure M star of union n is equal to 1 to infinity is less than or equal to summation n is equal to 1 to infinity M star of A. Before going to the detailed proof, which is quite easy, I would like to draw your attention to two facts. One is that in the hypothesis, I don't consider the collection to be disjoint. Countable collection of subsets. These ANs can have some intersection. We don't bother. Secondly, in the conclusion, it is not equal to, it is less than or equal to. So please keep these two things in mind. We are having any countable collection and the outcome is M star of union is less than or equal to summation of M star. This is usually referred to as countable subadditivity. M star is countably subadditive. For any countable collection of subsets, you have outer measure of the union is less than or equal to sum of the outer measure of the individual. Let me prove it. If an is such that m star of an is plus infinity for some an, there is nothing to prove. If m star of an is equal to plus infinity for some n in n, the result is obvious. Then there is nothing to prove. Yes or no? Do you agree?
Yes, sir.
In that case, the right hand side become infinity. I don't bother about left hand side. Whether it is finite or infinity, I don't bother. Okay. In fact, it will be infinity because union contains an. And monotonicity will give you that once m star of an is plus infinity, m star of union an will also be plus infinity. Okay. So let us assume m star of an is less than plus infinity. That is finite, I mean, for all n. Okay. Now, somehow I want to estimate outer measure of the union. You call this as set E, union as set E. To estimate outer measure, I need to take a countable family of open interval covering it. And then I have to find sum of length and so on. Okay. And I have to relate the m star of union with m star of the individual. So a natural question that we should ask is whether a countable collection of open interval that covering single ANs if I take, from that can I get countable collection of open interval covering the union. From the covers of the single elements ANs, I would like to get covers of the union and then I want to relate. Okay, so that's the idea. Central idea is that. Is it clear?
Yes, sir.
So I have to take covers for AN and then I have to from that I have to find a cover of union AN. Okay, that should be easy because you know that countable union of countable sets are countable. So that's what we are going to use. Anyway. Now, what is m star of AN? Basically, it is an infimum. Okay. Recall that m star of AN, fixed n, I am fixing AN. M star of AN is equal to summation length of I is equal to 1 to infinity, infimum taken over script I AN. The collection of all countable family of open interval covering AN. Okay, that is what script I AN. So this is what I have to do. M star being infimum, nothing more than M star can be a lower bound. Yes or no?
Yes, sir.
So M star of AN plus some epsilon dash if I take, that cannot be a lower bound. Now what do you mean by something is not a lower bound? In this, you can find an element less than it. Okay. So I'm going to use the definition of infimum. Okay. Since M star is infimum, given epsilon greater than 0, there exists an element in this collection, script IAN. There exists a countable family of open intervals, which I will write as I, N, I varying from 1 to infinity. This N is for a fixed AN. Countable family of open intervals I, N, I, such that it covers AN. AN is contained in union INI, I is 1 to infinity, and M star of AN is less than summation I is equal to 1 to infinity L of INI, sorry, M star of, I'm applying the definition of infimum. So nothing greater than M star of AN can be a lower bound. And summation I is equal to 1 to infinity, length of INI is greater than or equal to M star, sorry, less than or equal to M star of AN plus something, which I take as epsilon by 2 power n. Basically, M star being infimum, M star plus some epsilon dash cannot be a lower bound. That means there exists a element in that set with this value less than M star of A. That's what I have used. Nothing more than that. Okay. Is it okay?
Yes, sir.
Now, INI, I varying from 1 to infinity is a countable family that covers AN, a fixed AN. Now, from that, can I get a countable family covering union AN?
Yes, sir.
What will be that? Unions of INIs,
Yes,
right?
sir.
So let me write like this. The collection INI, IN comma I, N and I both are varying now. N is a countable collection, covering union AN, n equal to 1 to infinity. Because for each fixed n, INI, I varying from 1 to infinity covers AN. Now you take the union of that. Okay. Countability, because countable union of countable set is countable. Therefore, M star of union n is equal to 1 to infinity. By definition, it is infimum. This is less than or equal to summation NO I varies length of INI. This is one particular collection covering union AN, and M star is infimum. And this is equal to summation over N, summation over I, length of INI. Okay, that is equal to summation over N, length of INI is less than or equal to. So this is less than or equal to, this is M star of AN plus epsilon by 2 power n. That is equal to summation over n, M star of AN plus, this is a geometric series when n varies. And I think the value will be epsilon. 1 by 2 plus 1 by 2 square plus etc. That will be 1. Since epsilon is greater than 0 and arbitrary, we have M star of union is less than or equal to summation n M star of A. Okay. So we have proved the countable subadditivity of Lebesgue measure. Is that what you are expecting for a good measure? If something has to be called as a measure, what do you expect? Is it that subadditivity or countable additivity? Which one you expect?
Countable activities.
If you recall, I have told that one desirable property which we put as axiom for a general measure is that mu of union an should be equal to summation mu of an for a countable disjoint family. Here I have not taken disjoint. So you may feel that that may be the culprit, or that may be the reason for getting this only as less than or equal to. Okay. So your expectation may be that if I would have started with a countable disjoint collection, then M star of union an will become equal to. Okay. That is the expectation. We will see whether that will be true or not. So what I want to tell you is that as of now, our M star, the Lebesgue countermeasure, doesn't fit for a good measure that we want, because a good measure should be countably additive. That is not proved yet. Before doing something related with that, let me go back to the previous result. In the previous result, we have told that countable, let me put in this way, E subset of R countable implies M star of E equal to 0. And we have seen M star of Q is 0 because Q is countable. And we have seen M star of R. Let us take two specific sets. Q is countable and R is uncountable. What is M star of R? Because R is an interval, it will be same as length of interval minus infinity, infinity. And that is defined as infinity. Okay. So, outer measure could distinguish two types of infinity, that is countable infinity and uncountable infinity, as far as Q and R are concerned. Q is countable and M star of Q is 0. R is uncountable and M star of R is not 0, it is something else. So as far as Q and R are concerned, M star distinguishes countability and uncountability. Do you agree?
Yes, sir.
However, is it true in general? Suppose I take any uncountable set, can I say that M star will be always non-zero? For countable, M star is 0. For uncountable, can I say M star will be non-zero? So that's the question we want to answer now. Okay. Whether the question makes sense, forget about the answer.
Yes, sir.
What's the question?
Yes, sir.
Can
We want to see for uncountable.
for an uncountable set, can we always say that outer measure will be non-zero? If that is the case, we will be happy because countability and uncountability can be distinguished with the help of measure. Countable is negligible, measure is 0. And if it for uncountable, measure is non-zero, then we will be happy. Okay. So let me ask the question. Can an uncountable set be of outer measure 0? If yes, it is an unpleasant situation. For countable also, measure is 0. For some uncountable also, measure can be 0. If that is the case, then it is an unpleasant situation. And answer to this question is yes, unfortunately. Answer is yes. You can have uncountable sets whose outer measure is 0. So in that sense, measure is not good. Outer measure is not good. Uncountable and countable, both are different. One is more infinity than the other, but both gives you the same output. Outer measure is 0. Okay. So how to construct? At least one uncountable set I should give whose outer measure is 0. And for all such counter examples, if you remember in real analysis, there is a one peculiar set which serves as counter example for many things. Cantor set. So let us take that example. Okay. Example, Cantor set. Let me quickly recall what Cantor set is. Consider the unit interval Cantor to be specific ternary set. There are several types of Cantor set. I mean the Cantor ternary set. Consider the unit interval I will call it as E naught. E naught is equal to 0, 1. Can you recall the procedure to get Cantor set? We will divide this into 3 subintervals, 0, 1 by 3, 1 by 3, 2 by 3, and 2 by 3, 1. And we will remove the middle third open interval. Okay. Remove the segment open interval 1 by 3, 2 by 3. And let what is left is E1. E1 would be equal to 0, 1 by 3 closed union 2 by 3, 1 closed. Okay. Now do this. Remove the middle thirds. Remove the middle thirds of each of the interval. In E1. E1 contains 2 intervals. In each of them, remove the middle third. So 0, 1 by 3 is one part of E1. 2 by 3, 1 is another part of E1. Divide into 3. So it will be 1 by 9, 2 by 9, and remove this. And here it will be 6 by 9, 7 by 9, 8 by 9, and 9 by 9. And remove 7 by 9, 8 by 9. This procedure you know. And what is left over is E2. E2 is equal to 0, 1 by n, union 2 by 9, 1 by 3, union 2 by 3, 7 by 9, that is 6 by 9, 7 by 9 actually, union 8 by 9, 1. And do this, okay? Continue in this way. Continuing in this way, we obtain a sequence of sets. We obtain a sequence En. N in N. What are the properties? Let me write one property. E1 contains E2, contains E3, contains and so on. So it is monotonically decreasing sequence of sets. And 2, each En, if you consider, each En is the union of how many intervals are there? E1 contains 2, E2 contains 4, and so on. In general, En will be the union of 2 power n intervals. Each of length of each of those intervals in En is 3 power minus n. Okay. And you can also see that each En is compact, being finite union of closed sets. And in fact, they are compact. The set C will be intersection here. You take this monotonically decreasing sequence and take the limit. Limit will be the intersection. Intersection n is equal to 1 to infinity. That you call as C, and this is called the Cantor set. Called the Cantor set. And you might have seen several properties of this Cantor set. First property come to our mind is that Cantor set, whether it has some points, because you are removing many things. Finally, whether it will have point. Yes, of course, all the endpoints of the interval will be in the Cantor set because you are not removing it. So this 0, this 1 by 3, no, 1 by 9, all these things will be points in C. In fact, C contains uncountably many points. Okay, I don't know whether you have proved this. If yes, okay. If no, please try to prove it. C is uncountable. Even after removing many intervals, the number of points in C will remain uncountable. Okay. So it is an uncountable set. Our interest is to see what is its outer measure. Okay. What is M star of E1? Can you tell me?
Length of E1.
No. E0 I can say.
E.
M star of E0 is length of E0, which is 1. Okay. And M star of E1, apply the previous result. M star of E1 is M star of what is E1? 0, 1 by 3. 0, 1 by 3 union. Can you tell? Each time I have to scroll. 2 by 3, 1.
2 by 3, 1.
Okay. And you have proved subadditivity. M star of union is less than or equal to sum of the M stars.
Sum of.
This is less than or equal to M star of 0, 1 by 3 plus M star of 2 by 3, 1 by the previous theorem, subadditivity. Okay. But these are intervals. Therefore, M star will be length. Okay. That is equal to length
1.
of 0, 1 by 3 plus length of 2 by 3, 1. Okay. And that will give you 2 by 3 square. 2 by 3 square. Okay. Similarly, you can proceed in a same way. Similarly, M star of En would be less than or equal to. En will contain 2 power n intervals. Each of length is 3 power minus n. Therefore, M star of En will be less than or equal to 2 by 3 power n. Do you agree? Do you agree with this fact?
Yes, sir.
Because it contains 2 power n intervals and each is of length 3 power minus n. Okay. So again apply subadditivity, you will get. So M star of En is this for all n. Now, yes. M star of,
Sir, there should be 2 by 3 only. You took square. E power E1.
even it should be 1 by 3 plus 1 by 3, right? Sorry.
Yes, sir. 2 by 3.
Yes, sir.
1 by 3 plus 1 by 3. Yeah, thank you for that. And similarly, you can see that M star of En will be this. Yeah. Now M star of C should be equal to M star of C. The Cantor set by definition is intersection En. N is equal to 1 to infinity. Now again use monotonicity. M star of intersection will be less than or equal to M star of each En. Because intersection is contained in En. If A is contained in B, M star of A is less than or equal to M star of B. And M star of En is less than or equal to 2 by 3 power n. And this is true for all n. So M star of E is less than or equal to 2 by 3 power n for all n. So something like 0 less than or equal to M star of C is less than or equal to 2 by 3 power n for all n. Now sandwich theorem. 2 by 3 power n tends to
0.
0.
0.
Infinity. And that will imply that M star of C is equal to 0. Unfortunately, this is an unpleasant situation. C is uncountable, but still M star is equal to 0. So in general, countability and uncountability you cannot distinguish with the help of zero and non-zero of the M star. Did you get my statement? Countability and uncountability cannot be distinguished with the help of zero and non-zero of the outer measure. Countability will give outer measure 0, but outer measure is coming to 0. You cannot conclude immediately that the set will be countable. Even uncountable set can have outer measure to be 0. Okay, so that is an unpleasant situation. Forget about this counter example. Let us give me just 2-3 minutes. So far, we have defined the Lebesgue outer measure and we have given some nice properties of outer measure, which is consistent with properties of length, like monotonicity, translation invariant, and so on. Okay. But this nice property that I have listed so far should not lead you to think that outer measure has all the properties that we are looking for a measure. If outer measure was a good enough measure that extend the length, we expect that outer measure of union of disjoint sets is equal to sum of outer measure of individual. Yes or no? That's our expectation.
Yes, sir.
Yes, sir.
Please mute. If outer measure was a good measure that extend the idea of length, then we would expect outer measure of union of disjoint set is equal to sum of the outer measure. Unfortunately, that is not happening. Okay, so that with that I will stop. So let me put a remark. We had several results that tells you about nice properties of measure, outer measure. Results giving nice properties of outer measure. However, if outer measure were a perfect way to assign measure of a set as an extension of length, then what we would have expected, extension of length, the outer measure of union of, forget about countable, union of two disjoint sets would have been, would be equal to outer measure of sum of outer measure of sum of outer measures of each set. But this will not happen. So that is our next theorem, whose proof I will give in the next class. Theorem. That means this is not happening. I can find two disjoint sets A1 and A2 such that M star of A1 union A2 is not equal to M star of A1 plus M star of A2. There exists disjoint subsets A1 and A2 of R such that Lebesgue countermeasure of the union is equal to Lebesgue measure of A1 plus Lebesgue measure of A2. I can construct two sets not equal to. One thing you know, M star of A1 union A2 will be less than or equal to M star of A1 plus M star of A2. In fact, it is true for any collection, countable collection of sets. Even disjointness is not needed. But you will not get equal to for a pair. Such a pair I can construct. Okay. So this I will prove. This is not that easy. It needs axiom of choice. Do you know what is axiom of choice? Or at least can you say an instant where you used axiom of choice?
Yes, sir.
Can you tell me one instance where you proved something using axiom of choice? For instance, do you know the result that every vector space has a basis?
Yes, sir.
That result uses either Zone's lemma or axiom of choice. Anyway, both are equivalent, Zone's lemma and axiom choice. So I will suggest you to recall what is axiom of choice, why is it so called axiom of choice, and why is it so important, and how is it equivalent to Zone's lemma. And please keep in mind that whenever a result uses axiom of choice, it is existential proof. It is not constructive proof. Something exists, you can prove by using axiom of choice. And how to construct it and where is it, if you ask, I cannot do that if a particular proof use axiom of choice. So if you see, there are two types of proofs. Suppose you wanted to prove that something exists, you may show it, here it is, and then show that yes, there exists. Sometimes you may not be able to show that here it is, but you may be able to show that such a thing exists some other means. That type of theorems are called existential theorems. Okay, and the proofs, if the existential theorem uses axiom of choice, then the proof will be just existential proof, not constructive proof. Okay. Constructive proof will construct the object in question. Existential proof will tell you that somewhere, somehow it exists. Is it clear?
Yes, sir.
Yes, sir. Yes, sir. Sir, you are muted.
You have a theorem there exists, see the proof and carefully watch whether the theorem proof construct the object or it is just shows that it exists by something like axiom of choice or not. Okay, if somewhere it is used axiom of choice, then it is not a constructive proof. It just say it exists. Where? I don't know. It's something like God exists. You believe or don't believe. That is up to you. In fact, there is a small community of mathematicians who don't believe axiom of choice. They don't believe axiom of choice. Okay? So in that cases, such results are not valid for them. Like every vector space has a basis, etc., are not valid for them. So axiom of choice is really debatable, and there are so many things. It is very abstract. You should think of why this and what branch of mathematics does not accept axiom of choice and so on. Anyway, so with that, let me stop. Thank you.